Great, so let's get started, everyone. Okay, so this is the last lecture of new content for the semester. The plan is to try and go through some important examples of other types of classifiers beyond the ones we've done in class. So the ones we looked at so far, we could mostly derive from first principles and understand them, pretty clearly. So the ones we'll talk about today are ones which are, in some ways more powerful, but are, so hard to understand. So when and why they work. So there are, and so there's actively work in trying to build the same sort of understanding that we've had for like linear classifiers and kernel SVMs for these more advanced, sorts of classification. It's not necessarily a very simple theory at the level of like the junior level course. But I will, try and, build on what we've done so far in the class to kind of explain things like these, k-nearest neighbor classifiers, decision trees, which lead into random forests, and neural networks, which you'll see actually, the ideas there are kind of a direct extension of the things we've done, but are more complicated in a variety of ways. Okay, so before we get started, I want to say, see where we are in the schedule. Quiz. At this point, quiz. 6 should be graded. You should have gotten the grades for that. They should be finalized. People did fairly well. There was one question we felt was not phrased very well, so we just gave everyone full credit on that. And so there are a couple of versions of it, and some were less clear than others. We just gave full credit to everyone. So the grades are pretty good on quiz 6. Homework 4 should be graded as well. Homework 4 is one of the more challenging homeworks. So the grades weren't as good, but I'm overall happy with, the number of people who've done, so well in homework 4. Yeah.
Assignment work.
There is so you get to drop the lowest grade for your homework, but you can only do that if you have made an attempt on, all the homework. So you can't not do homework 5 if you think you're doing well. If you didn't do homework 4 and we're hoping to drop it, well, you can still drop it, but you have to, actually do it. If you didn't turn it in by the deadline, I will let you turn it in up to when I turn in grades. But you have to at least attempt all the homeworks if you're going to drop one. But that's built into Canvas. The Canvas grades automatically drop homeworks. We're going to go through and see if people didn't turn in a homework and let them know that that'll have to undo that drop if they don't, make an attempt on it. But the lowest homework grade will be dropped. Each of the quizzes is only worth like 3.5% of the grade, so I'm not dropping any quizzes. Yeah, so okay, there's one more homework due, basically the last day of the semester. So it's due on this Friday. If maybe I'm not supposed to assign something due on this Friday, then you can say it's due on Thursday instead if you'd prefer. I think that's still enough time to get everything done, but I'd like to give you as much time to finish that as possible. And so we can at least discuss the answers if you have questions after the late deadline before the final exam. Our final exam is fairly early this year. It's going to be on next week, Monday, which is coming up pretty quick. So we still have to make the final exam. So I'm planning. so I'm planning to make an announcement to explain this. I've been, so debating what to do for the final exam. My plan is to have it as a Canvas quiz. All right, and it will open at 10:30 on this day. I will leave it open until the end of the day. Okay, so you can take it flexibly with your schedule. But I'm a little, when you have a Canvas quiz, it increases the likelihood that someone out there or some people might get together and try and cheat. I don't want you to cheat on it. I don't want you to work together. It should be done individually. I will be here. I recommend you do it here in class. Then we can answer questions if they come up. So I'm going to add in a feature, unlike the quizzes, where you're going to see one question at a time. Okay, I know this is not as much fun. You can get frustrated on individual questions, lose track of time. You're going to have to, we'll let you know how many questions there are, and you'll have to try and pace yourself on that. Yeah.
Will it be like if you answer the first question, you can't go back?
Yeah.
Oh, God.
So our plan is to, otherwise you go through all of them and then you can sit together and work on it together. And I can't, it makes it too easy to cheat. Right. So, and it's the final. So our plan is to make the final as we would normally. And last year people did very well in the final, and then to make it 10 to 20% easier to account for the fact you can't go back to questions. Okay, so I realize this is not fun to only have one question at a time, but I hope that it's going to cover everything in the semester and the questions are going to be fairly straightforward. So it'll be okay to go through. I think that, last year we had 15 questions. Okay, so you have 2 hours. So it's going to be kind of like 4 quizzes, so stuck together. Okay, I expect it to be like on most of the last few quizzes, the average grade in the class has been above 90%. I expect to start there and then to make it, try and figure out what are the most tricky questions, take those out, add hints so stuff is obvious. I don't want it to be hard. And I'm hoping to compensate for the fact that you only see one question at a time. Yeah.
So it's very much like this. Here's multiple choice. Here's fill in the blank. Here's full.
Yeah, it should be like that. It should be like I'm aiming for it to be like the quiz questions where the class did, very well on these, on these questions. You'll be able to have notes and open book, but you'll have to pace yourself. But our aim is to make it so that, like a lot of the quizzes, the ones that we kind of were on the easier side, you'll easily, almost all the class will finish, in roughly half the time, and then to be a little bit easier, right? So time should not be an issue for most of the class, right? There's always some people who wait until the last minute, but it's going to be, these are kind of trade-offs. There will be some true or false questions, yeah. But we'll have more questions. So like a true and false questions might be worth like 2 points or something, right? So on some of the quizzes, like you're given a trickier true or false question, it's worth like 15, 20 points. You get that wrong, it feels like a big drop. So like you might have like, okay, here's a topic, here's a couple of simple, instead of saying, pick which ones do it, does this thing, is this thing true or false, instead of pick the ones which are correct, sort of thing, right? So there are a number, so we can kind of break down the grade in some way, yeah. Yeah, so anytime there's kind of like a blank, you can show your work in the blank. If we think there's something that people might want to show extra work, we will try and make some way available. Our aim is going to be things where you're not going to really need to show your work to do most stuff, right? It's going to be, things you don't have to do a lot of, so calculations. Yeah. Correct. It'll be broken into a block of, it might be 15 questions total, and each one will be self-contained. It might have multiple, say, true/false questions in it, right? But it's for one of the, say, if there are 15 questions, right, then one of them might have 3 true/false questions as part of it. Right, so the Canvas allows you to do stuff like that. So I was looking over how we did the quiz last year, and we had a couple of questions like that. Yeah. Yes, that'll be the same for the final. You'll be able to upload notes. You could take, if you had really good kind of cheat sheets for all the 6 quizzes, you can upload them. You can have a PDF document or whatever, so sort of ready. You can upload 6 pieces of paper or 1 PDF with 6 pages, and you can get up to 6 points back. If you might want to refresh and add some stuff on there, we will score based on if we'll give you a score proportional to the amount of stuff you did. So some of you did not always get the full 5 points, then you might want to add a bit more onto your cheat sheets in order to get the full 6 points you would get back in the final. You can get up to 6 points back in the final with the cheat sheet, up to 6 pages. Again, it could be the 6 things you've already have just stuck together, but you can redo those, and that would be a way to study. All right, another question?
No, my question.
Oh, okay. Yeah, okay. So I kind of, I anticipate it. Our aim is that it's going to be not too hard. We're going to put in this thing in there because, otherwise, if I have this open 20% of the grade this way, I wasn't willing to kind of, have that trade-off. But I don't think time will be an issue. We will work hard to try and make sure things are clear. And then you should be able to, fly through it. Yeah.
So we have 2 hours for take test.
Once you start it, you have 2 hours to finish. Yeah, and I'll recommend you do it here. We'll have this room. The TAs and myself will be in this room to answer questions. We'll also be on Zoom during this time from 10:30 a.m. to 12:30 p.m. Yeah. Yeah, so it's totally open book. Don't anything that's kind of a direct resource of the class. I don't want you to kind of be using a question answer site and stuff like that on the internet, right? But the book, the class notes, so stuff like that. I actually don't totally recommend you use like Wikipedia and other sources because there is some difference in notation and these things, and what we use in the class is usually pretty standard, but it's not always exactly the same thing. And so I actually recommend you stick to the material directly associated with the class. Everything on the final should be associated with that. It will cover everything in the whole semester, right? I believe this class is really, I think this class is really built on the material. We've added layers and layers of stuff. And I think when you go back and look at the earlier material, you'll find it will be much more easier and intuitive now that we've gone and been using all these tools kind of later on this semester. Okay, so I think the earlier parts of the semester are going to be much easier than when you were first taking the quiz on. All right. So that's my hope. If I've done a good job teaching, that should be the case. Okay. Oh yeah. Will the example exam be fairly similar to the type of questions we'll see in the exam? Yeah. Okay. So there is an example exam practice down here in the bottom right corner here. Okay. Oh, this is on my iPad. Mouse won't work. Okay. Let's. That's here. There are a bunch of questions that covers the entire semester worth of material. There are 16 questions here. Okay, these questions are these questions I think are more challenging than what will be on the quiz. There are definitely some tricky questions on here. Okay, so this one has some questions that make you think. You might not actually get it. If you can do well on this, you're going to do well in the final. The plan is for the next lecture is that I'm not going to like publicly post the answers to these, but I'm going to do the next lecture on Thursday. I'm going to go through all the answers in class. Okay, so that's my plan for on Thursday. I suggest you look through that and you try and think if you know what the answer is beforehand. Go through the whole thing. You can write it out as much as you want, or not. And then in the class we will go through everything. Right. So this is a harder version. It's probably going to be harder and longer than the quiz you'll actually take. And we will go through all the answers in the class period we have, which is less than the exam time. Okay, so but you know, I know all the answers, so I can go through them quickly. You may have to think. So I understand that. But so that's the plan for Thursday. Yeah. Okay. Yeah, it will be recorded. You know, and I did the same thing the last few years. So in fact, you know, you can also find those lectures, but you know, I might add some extra, you know, so sauce this year as, you know, as usual. So, so okay. So any other questions on the final? All right, I think things will be fine in the final. I will make clear ahead of time. I'll let you know how many questions will be on it. You'll be able to see the kind of the so like the total number of points will add to 100. So you'll be able to get a sense of how you're doing. So well, we still have to implement that so that works. I'm pretty sure I know how to get this to work, but we'll figure this out over the next week. So okay, great. So let's get into the lecture. All right. So we're looking at classification, right? Just to remind, classification. Okay, so the input is going to be so X, so Y, and this will be a subset of R D cross -1. So in +1. So so data point Xi, so Yi is going to be an element of RD. So that this will be Xi this will be Xi and -1, so +1. This will be the value Yi. And so we're given these vectors in kind of d-dimensional space, and they're given a sign. And the goal, so the goal here is to build a function f from our D to -1, so +1, and we typically implemented this where f of x is going to be the sign, so either -1 or +1 of a function, so g of x, where g of x is from RD to the real values, and we're just saying, okay, if g of x, if for this point it's positive, we're going to predict it's a +1. If the value is negative for that x, we're going to predict a -1. That's what we've worked at, you know, so far. The first two methods we're going to look at are going to directly build this function f of x, which is just giving us the sign. It's not doing this proxy function first that we snap as the sign positive or negative to get the class. Okay. Okay. So the goal is to build this function So new data, right? So if I get a new, so data point x, y drawn from, you know, some function mu and x, y, this, so the full data set, let's say this x prime and y prime, that the full data set is so also from this mu, so IID. So we assume that the data was drawn IID from some sort of distribution. And if we get some new data point, x prime and y prime from the same distribution, that f of x prime is going to equal, so y prime. Okay. So say with, you know, so like high probability. All right, so it may not always do that, but we want, so a high probability that we're going to have the function is going to predict, you know, the right value, right, is going to predict the right class here. Okay, so this is what we want. We want to build some function, then our new data is going to work well, right? And so the basic approach we had looked so far is we had built a function g of x, right? And we may have split the input into a training set and so like a test set. And so we could build the function g of x, maybe the best from a class of, say, linear functions. This was a convex problem on the training set, and then we can maybe tune some parameters on the test set or evaluate how well it's working on the test set. Because we assumed everything was IID, we could split, and both the training and the test set are going to be some representative examples. Okay, so we want to keep, this is the big picture for classification. I'm going to talk about kind of a variety of other approaches to this problem. Given that this is our general goal, we don't need to go through this function, so g of x anymore. Okay, so kind of the first variant I want to talk about is k nearest, so neighbor, so classifier. So this is often called a KNN, okay? And the idea here is that we're given a, you know, so set of points, you know, so each of these is xi, and there's the set x, which is an RD, okay? And then on a, you know, and each of these points has a, so like a label associated with it. Okay, and it's either a plus or a minus. So those were the minus points, the red ones are the plus points. Okay, and then I'm going to issue a query. So query could be x prime, and then I'm going to, so k is going to be a number here. Let's say, well, let's do k is equal to 5. Okay, so 5, I'm going to find the 5 closest points, and let's say those 5 closest points are going to be, you know, I can draw, if I draw a circle around x prime, okay, I draw a circle around x prime, and I keep making that circle bigger until it includes, so 5 points, right? So these are the 5 closest points, okay? And then I'm going to, vote. So I'm gonna say that these are, so this set of 5 points, these 5 points inside the circle, I'm gonna call this, say, a set x, I call this x prime k, which is going to be a subset of x, okay? And then I'm going to vote on the signs, in sk of x. Okay, and so I'm going to have 4 plus, and I'm going to have 1, so minus, and so it's winner take all. So I want k to be an odd number so that I don't typically have ties. And there are more pluses than there are minuses. So my prediction is going to be, so then f of x prime is going to be, so plus. Okay, and so for each query, I have to issue this kind of, this retrieval problem to find, so the k-nearest neighbors, and then I look at the sign of these points, and so that's, going to be what the prediction is. Okay, yeah.
So is x prime one of the points in x, or is it just the
Yeah. So no. So this one's is, so this one's going to be a query. Okay, so again, the goal was, so on new data that I haven't seen before, that my prediction is going to be close, assuming it was drawn from the same underlying sort of distribution. Yeah.
Is it for common?
Oh, so in case you're not sure, you want to report some sort of uncertainty, that is possible to do, but it's not common. Usually, whether you should do that or not, you should say, I'm not sure, so I'm going to pick an even number. So if there are ties, I'm going to let people know that there are ties. Yeah, unfortunately, most people, when they use classification, they actually want an answer. And so they don't care about what it means. They just say, okay, here's the prediction. And with ties, that becomes, so much messier. Just look at the World Cup. There's all these extra rules having to do with ties. It's easier if you just say, okay, there's either, just a winner or a loser. Maybe the World Cup, if there are ties, then you have 3 classes, right? So you have the positive, the negative, or maybe you predict a tie, but then your labels are also like that. So it's actually much more complicated. Yeah, so this is a completely different sort of classifier, but it fits all the criteria we had on the previous slide. Okay, this kind of is like outside of the realm of how a lot of other things work, but it's sometimes a very useful and so powerful classifier. One interesting thing to is to keep in mind here is this works for any notion of distance from the query. I've defined the 5 closest points using the Euclidean distance. But if I had objects where I had like strings of text, and I want to say how similar are these strings of text, like are there typos in the text? I measure like the edit distance, number of edits I need to make between 2 strings of text to get from one to the other. Edit distance is a way of measuring distance, and I can use that inside this classifier. It works totally fine. Okay, so I can change up the distance and everything still works. So it's kind of flexible in that way, and that I don't need to think of things as vectors anymore. As long as I can compute distances, I can use this classifier. So it's kind of powerful in this way, and it's kind of outside the box. So, okay, great. So this is all I'm going to say about k-nearest neighbor classifiers. It's a very general approach, and sometimes it works extremely well, but this doesn't have to do with gradient descent or convexity or sort of anything like that. The next classifier I want to mention are decision trees. Okay. And this classifier now kind of assumes that, unlike before, this one has that the data X is going to be in RD. It could be a subset. It could be like categorical. Actually, you can encode that in RD in various ways. Yeah, so this one will be flexible in other ways, kind of different from the KNN classifiers. And so the idea here, I think I can draw a picture if it's an RD. Let's say there are some points. So like this, these are some, so some positive points, and then so some negative points as well. Okay, and the decision tree is going to build a tree on these points, kind of like if you've seen like a binary tree, hopefully it's going to build something, but it's going to build a binary tree over so two-dimensional space. In fact, we're going to use something like a KD tree. If you've seen what that is, that's the right, so sort of analogy. And what it's going to do is it's going to kind of continually or recursively split this data set into two halves. Okay, and for instance, we had one more point down here. Okay, so one split might be, so I'm gonna, and it's gonna split on, so the coordinate axes. One thing nice about this, it treats all of the coordinates in a way that's different from all the other coordinates. So they can mismatch in units and there aren't any, there's nothing to worry there. So let's say this is y equals to 5. And so I'm gonna correspond that with the split in a tree. I'm gonna build up in parallel on the right side of this picture here. So this is y equals 5, and I'm going to think of two subtrees where this is y greater than 5, and this is y less than 5. Okay, and so I have two halves. And less than 5, it's mostly negative, and greater than 5, it's so mostly positive. And then I'm going to do this recursively. Okay, I'm going to recursively split again here. If I split right here on the top, this is y greater than 5. Right, let's say this is x equals 3. This would be x equals 3 here. And typically you switch between the coordinates, right? So then I'm going to have three cases here. X, this will be x less than 3. This will be x greater than 3. And when I got to this cell here, it's gonna get a plus, because everything in the cell corresponds to here is going to get a plus sign. Everything in there, all the data is plus. So I'm going to say, okay, I'm gonna, if I have a, if I make a prediction on some new, so data point, right? This is x prime. This is my query. Right, so what I need to do for f of x prime, I need to say, is it greater or less than, is the y value greater or less than 5? It's greater than 5, so it's going to go down in this way. And there's a greater or less than, the x value greater or less than 3 is greater than 3, so I go down here, and then I'm going to get a plus because I get down to this cell. Okay, so if, I'm going to say if I get into this region, I'm going to predict a plus. Okay, in this on this other side, I might want to split again, right? So I might want to say y is equal to 7 is this value, and split, here again, y is equal to 7, and have y is greater than 7 or y is less than 7, right? So if it's less than 7, I'm going to get a minus. If it's greater than 7, it's going to be a plus. Okay, and then I can do the same thing on, on the bottom as well. I could try and split this off. I would actually need to go down several layers. There's not, well, if I split on x first, I can't split this plus apart from the other minuses. I could go so further down. But the other thing I could do is say, well, at some point I can stop early. I don't have to get a perfect classifier. It might be good not to get a perfect classifier. So I might actually stop here early and say, well, if I get down to this region, I might say this is going to be a minus. Or I could, so possibly So keep going so that there's a plus, there's a minus. So, and there's a minus. I could also kind of fill this in, or I could stop early if I think, well, it's 6-to-1, the ratio is pretty good, right? So, okay, so there are a couple of questions. Yeah, go ahead.
So, minus that bottom one, you essentially using KNN for that bottom.
Oh, so then I would do voting at the bottom. Yeah. So if I think that the ratio is high enough, if I look at the voting and it's like a blowout, right? It's like, 80 to 20%, I can call the election before I count all the votes, basically, is what you're saying. I don't need to go further down. Maybe there is some chance that the true answer might be +1. Maybe that's because I refined it kind of geographically or regionally, like if something happened down here, it really should be plus, or maybe I say that's noise, right? So what's the trade-off between these two things, right? Why would I want to build the full tree and get perfect classifiers on the trained data versus why would I want to stop early? So what do you think? Yeah, so the computation time is faster if I can stop early, both in building this tree, because I build it from the top down, and also from actually making a prediction, right? To make a prediction, I need to trace down the tree, and if I can stop that early, then that's also faster, right? The trees could be much bigger than in this diagram here, right? Most trees, the depth are like log n if I do a fairly even split, right? So the evaluation time is not so much, but the size of a tree that is a perfect classifier might be, I might have to do a linear number of splits in order to get an actual perfect classifier on the training data. So if I can stop that early, that might, that could save me some time. Okay, so what are some other reasons I might want to do early stop? I could overfit. Yeah, so if I did continue on here and split here, and then I split again, I might kind of be overfitting. Maybe this really is all negative points down here, and there was just a stray outlier, but now I have this whole region down here that I'm predicting as, so as positive, right? So this could, if I do a perfect classifier, this could like, do like overfitting on the data. And so typically with a decision tree, you will, if you think that there's going to be some noise in your data, you will set the maximum depth or the maximum kind of number of splits, or some other criteria. Yeah. So any other comments on why I might stop early? Everyone had the same idea, which is great. Yeah. So you can overfit. So that's the main reason that you would stop early. Okay. One other thing we need to say is how to split. Okay, so what do you think is the right way to, choose how to do a split? Yep.
Count up all the classifiers in each box, split wherever you can find a linear classifier.
All right, so let me write this down as choose, the best one, right? There might not be a linear classifier. If there was a linear classifier that I had all the positives on one side and all the negatives on the other, I definitely want to do that. That only happened twice. That only happened at the bottom layer here, and then in the left part at y = 7. Most times I didn't have a perfect linear classifier, right? If I have one, I probably want to do it. There might be another criteria. I might want them to be kind of balanced because I want the tree to be roughly height, so log n instead of linear height, right? I could keep trimming stuff off the outside, but I'd rather have some sort of balanced split. But so I want to choose the best split in some way, right? At every layer. And I could, in this case, with just 2 coordinates, you probably alternate between the coordinates, although you don't have to. With more coordinates, there's kind of a choice too. I need to pick the coordinate and then pick the split. And so typically what the method will do is it will kind of consider all possible splits at that stage and pick the best one. So I somehow need to choose the best split by some sort of criteria. If there is a linear classifier, a perfect classifier, I should probably do that, right? But, so what is I have to somehow choose the best split at each stage is typically what, is done. And so the way this is, there are a couple of somewhat standard ways. The most common way is using what's called, so the Gini index, or source, sometimes called the Gini impurity index. Okay, and what I'm going to kind of score an actual split that I make. Okay, so let's say, I'm looking at the first split here. Well, let's look at this particular split. And I'm going to say, how good is the top part here, right? Well, let's look at the top part, and I'm going to create two quantities. Right, so let's look at this index for the split. Let's look at the top part here. And so P plus is going to be if the number of plus points divided by the total number of points. Okay, so this is going to be 6 in the top part, right? It's going to be 6 divided by 8. 6 divided by 8, right? So let's look at, for this, compute this for here. And then similarly, I'm going to compute P minus, okay, which is going to be the number of negative points divided by the total number of points. This will be 2 over 8. Okay, and then this index G is going to be P plus times 1 minus P plus P minus times 1 minus P minus. Okay, so what is this? So represent, sort of intuitively, it's the probability that I'm going to, there are kind of two parts of this. First part is the probability that if I picked a random point from this region, it's going to be a plus point. That's this first value. This is the probability is going to be a plus point of all the points in this upper half. The probability it's a plus point is going to be 6/8. So 0.075. And the probability it's going to be a minus point is going to be 0.25, 2 out of 8. Okay, and then I'm going to say, what's the probability I misclassified that point? That's 1 minus that, right? So the probability, I'm going to get 0.75 probability I selected a plus point times the probability it's misclassified, right? So that's 1 minus 0.75. Okay, that's the probability I picked a plus point and I misclassified. Okay, the probability I picked a minus point is 0.25, which is lower, but there's a higher probability that it's been misclassified. Okay, so I'd like this to be as small as, and so this is the overall probability that a point from this region has been misclassified. And I'd like that to be as small as possible. Okay, if it's very pure, meaning that it's all plus points, right? Then if it's all plus points, then P plus is going to be 1. 1 minus P plus is 0, right? So I get 0 probability misclassified. The probability I pick a minus point is 0, right? So that the second term is also 0, and the Gini index is 0. So I want this to be small. If it's 50-50, what happens? If it's 50-50, I get 0.5 times 0.5 plus 0.5 times 0.5. I get a value of, so 0.5. So the more like mixed it is, then the higher the scores, the more kind of concentrated towards one quantity, it's going to be a smaller value. If I calculate 0.75 times 0.25, that's going to be 3/16, right? Plus 3/16, right? So that's going to be, this is going to give me 6/16. Okay, so this is in between 0 and 0.5. The smaller, the better. Okay, so this is less than 0.5, so this is better than an even split. So I want to kind of, I want to choose splits so that the average the average score of the Gini impurity index is as small as possible across both of the halves. Okay, so this is probably the most common way to choose the splits. Trying to compute this measure and then pick the split that minimizes this. Yeah.
So this number doesn't necessarily take into account that, like, your data, like, subcategorized too many times.
Yeah, so
Let's see that.
not in just using this. This would tell you eventually you want to have a perfect classifier, right? But you would try and capture that by limiting the number of total splits you do, or the total depth of the tree. Make sure it never splits more than so many different times. Yeah.
And then maybe it wouldn't have enough many splits to the bottom. So it'd be really good at top other portions.
So yeah, so there are some, there are some issues with this. This is the most common way. There are others that try and enforce some balance of the splits, or some other criteria. But typically, so this is how it's used by itself, right? If you think, okay, the top half, the top 4 of them, that's pretty clear. If I'm above that, I should say, okay, if I'm above the threshold y is equal to 7, then I should say it's always, going to be positive. That's a pretty simple rule, and I should encode that in my classifier. So you could also argue on the other side. Then, okay, now let's try and worry about the bottom sum. So that's generally how the algorithm works, right? It's the only kind of better ways people have done this is by changing this criteria, maybe to add something based on kind of you try and balance it. There's another version I talked about in the book, I won't write down, that looks at like the entropy. You're trying to look at the how much information you gain by doing this split. And you might gain more information by splitting in the middle, for instance, than by just cutting stuff off at the top. So there are other ways of approaching this, but this is kind of the single most common approach. Was there another question over there? Yeah, you could do that way as well. Yep. So there are a variety of ways of approaching this. Yeah. So okay. So what are the? Oh yeah. Go ahead. So yeah. So typically, it's gonna be a little bit slower because when you're choosing the split, usually you kind of sort. For every split decision, you pick each of the coordinate axes and you sort in that coordinate axis, and then you scan across in that sorted order and looking at all the splits, updating, the Gini index or another score. And you do this for all the coordinate directions. You don't look at linear combinations of stuff within a decision tree. So it scales kind of, it's linear in the number of coordinates you consider, which is not too bad. There are other things that could scale much worse in the number of coordinates, like the Voronoi diagrams and stuff grew exponentially in the number of coordinates. That's much worse, right? A matrix inverse is basically the number of coordinates cubed, right? So this scales pretty well in the number of coordinates. Yeah. So okay. So the biggest advantages of the decision tree are, one, it treats each of the coordinates so individually. So you can have mixed types of data. I can have some being kind of, feet, some measured length, some measure weight, some measure time. That's okay. I throw them all together. It can be some binary kind of vectors in here as well, right? One of the coordinates might be, so just binary. There's only one split to actually consider at each stage. But maybe after I split in other directions, how that split shapes up changes, right? So you can do a lot of, throw lots of data into this, and it kind of just works. So if this works, I don't need to worry about the structure of the data or mapping it into various forms. The other thing is that it's usually described as being so fairly interpretable. You kind of make this so like decision tree, and then when you make a query on here, it's also following these decisions, like one at a time. I can explain, so like there's been a lot of work and you're using, so healthcare data, you're trying to make a prediction on healthcare data. A doctor wants to use machine learning to try and say what's the best, what disease is this likely, how should I take a course of action based on that? And they'd like to be able to interpret how that decision was made, because maybe it was based on some data where there's these examples where, for instance, there are like x-rays of different people, and they tried to build a classifier on it, and the x-rays were taken from two different labs, and it kind of picked up on which lab the x-rays were taken from in the classifier, which should not be used if you use it outside of one of those two labs. That's something irrelevant, but the classifier picked up on something like that, right? And so it was not like a medical decision. It was picking up on stuff that was not going to be relevant. And so this way you can interpret, what are these actual decisions? What does the y coordinate mean? And what does splitting on 5? That could be, okay, if a patient is above 65 years old, it's much more likely that they have this sort of disease, which happens later in life, than if they're younger, right? And how you treat COVID, for instance, is very dependent on these sorts of rules. And this is a way of learning these simple rules. So it's quite so interpretable, more so than I would say a linear classifier, and much more so than the things we're going to talk about next. Okay. Before we get to neural networks, I would say decision trees are usually by themselves are not they don't. There are a bunch of these competitions. People say, okay, what classifier works the best? What does it generalize best on the data I've held out? The decision tree is rarely the winner. Okay, it rarely generalizes better than these other methods. It's more interpretable, but there's kind of this trade-off between like the interpretability and and how well they generalize is often the case. So you could think of an axis where, so in interpretability, and then this is generalization. Okay, and I would put things like, okay, the interpretability is going to be high. This would be like a decision tree. Okay, it's going to be out here. So something like a linear classifier is going to be something like here. Probably, I would say like this line would be a polynomial classifier. polynomial classifier. All right, so the interpretability, there's less interpretability, but it's really, maybe this is even maybe a kind of an angled line where it'd be something like this, where the higher the degree of the polynomial, the less interpretable it gets. And at some point, the generalization is better, and then you start overfitting, and it goes, back down again, and is less interpretable what's going on. Okay, there are things like so, and we're going to talk about things like neural nets, okay, which are going to be high generalization. They tend to do well on new data if you have enough data and so forth, but they're less interpretable what's going on, especially if they're more complicated. There's another thing why I want to draw this is there's another thing called a random forest, okay, which is also very low on the interpretability, but generalizes pretty well. It does well on these experiments. You try all these, you see how well they do on the test error, right? And the random forest tends to do quite well, but is not very interpretable. And these two are these are random forest and the decision tree are linked together. The random forest is I build a bunch of decision trees. Every time I build one, I randomly leave out a subset of the data or a subset of the coordinates. And I build a decision tree. I build a bunch of them, like 20 or 100, and then I average those decision trees together. And it's not a uniform average, it's kind of a weighted average, and I learn that weighted average, okay? And there's been a lot of progress in how to understand what's going on with like neural nets. In fact, that's why I moved more to the right. But the random forests are less interpretable, a lot of people have argued, and sometimes perform a bit better, depending on the data, right? Depends on different challenges, different ones perform better, okay? But so a random forest is based on a decision tree and is one of these things that works extremely well in practice. And they're pretty easy to use. You don't need to do a lot of tuning. You pick in some you can cross-validate this one thing based on the depth or like how many trees, but you can put coordinates in there, the coordinates can mismatch and everything just works. Okay, so it's a very easy to use thing from the software perspective, but how it works is not very interpretable. Okay. My personal view on this is that anything over here, I would label this as not so interpretable. Okay, anything left of a linear classifier, it's probably not interpretable, especially not from, maybe if you guys get a good understanding of these things and you can maybe kind of understand what's going on, and the more you work on it, you can kind of get better understanding. But kind of a doctor making a decision who's not trained in this, it's probably not going to be able to use anything more than a decision tree and maybe a linear classifier, okay? But a linear classifier, there's a lot of false interpretations of those as well. So I would, maybe it's maybe even kind of, over here. Okay, what is interpretable, what's not interpretable? People will argue with me on this. This is kind of my personal view of it. So I wouldn't worry too much about the interpretability. Once you get left of a linear classifier, it's probably not interpretable. There are tools you can do to kind understand it, but I'm skeptical of a lot of these things. Okay. Okay, so let's get to, neural nets. Oh, I did not leave myself a lot of time here. Okay. Okay, so the first thing you need to know about a neural net is this idea of a neuron. Okay, and a neuron is going to be something that takes in a vector x, say x1, x2, up to xd. Okay, and this puts it in some, think of this as a vector, and each of these as some values in the vector, right? So this is in our d here. And what it does is it pumps all these to a value, okay? And it makes the decision, is this total value greater or less than some sort of threshold? Each of these gets a weight 1 up to WD. So it has a value that's coming in here. You can kind of think of as values as coming into every element of the vector. And what the neuron does, right, it's going to have some sort of output. So threshold, either fire or so not, right? So a neuron, like in your brain, that conceptually, this is like your brain is made up of these neurons, and they take a bunch of stimuli input, and depending on how strong the connection is, it accumulates at some spot. And if that accumulation reaches some threshold, then the neuron fires and sends a signal forward. Okay? So we can write this down so mathematically, and we can say what is happening here is there's a sum j equals 1 to d over the xj times a weight j, and I want to know if this is greater than some threshold b. I can actually rewrite this. This is equivalent to w dot x, right? That's a dot product right there, minus b greater or equal than 0. So what does this look like? X is the input. Somehow there are some w's and threshold we have to set, which are the parameters. So the neuron is just, what if I wrote this as g of wb of x? Yeah, this is just a linear classifier. Okay, so the idea is that a neuron is just a linear classifier. Okay, so the idea is a neuron works like this linear classifier. What does the perceptron algorithm do? If I somehow learned I made a mistake, it should have fired, but it didn't. Somehow some signal gets sent back, right, on the example, and it updates, the weights proportional to the strength of the signal here. Okay, and it updates the weights. If I had a lot of signal coming into XD, and the weight WD was too small, and that's why it didn't fire when it should have fired, or vice versa, then it makes this weights larger. It says I should have paid attention to that. And to do this accumulatively across all the real values, that's exactly the perceptron algorithm. Okay, so the way of viewing how this is updated based on did it fire when it should have or not, when it observed data that it didn't fire or not, it made a wrong decision, it updates the weights based on the values. That is the perceptron algorithm. Okay? Okay, yeah.
I was wondering whether it fires or not.
Yep. No, so this is just a neuron so far. I haven't gone to like the neural networks. Yeah, okay, great. Yeah. Okay, so neural network, we're gonna draw this as kind of a triangle here. Okay, I need something else, right? You're right, it's hard to deal with binary values, right? We're gonna wanna optimize some weights and stuff, and instead of fire or not fire, we'd rather have continuous values here, right? So we're gonna put a a thing here that's going to be called it's like an activation function. Okay, there are a couple of common activation functions. Maybe we'll call it phi. So phi of one, we've seen this already. So the output here might be a value y, and it may have some offset with b, right? But let's say this is a value y, then the activation function, one example is the ReLU, rectified linear units of y, is going to be the max of 0 and y. Okay, so this is a function that is okay, we saw this as a loss function when you put in z in here. This is kind of like a loss function, but it was swapped. Okay, so this is a ReLU. If I have a value y here and this is 0, then I'm not going to return a negative value, but if it's large enough, then I'm going to pass on the exact value. If it's below that, I'm going to not send anything for it. Okay, this is kind of replacing a binary thing with something smoother that's so is going to be convex. Another common version of an activation function is going to be, let's say the sigmoid. Okay, and so there, this is 1 plus y, 1 plus x of negative y, this all over 1, or all 1 over that, that's okay. And so this is going to look, if I were to draw this one, the sigmoid goes like this. Okay, so it's kind of, it's between, this is going to value between 0 and, this is between 0 and 1. It's never going to be 0 or 1, but it's kind of rounding a smooth version of this threshold. This is not so convex. It's not a convex function, but it's so going to be differentiable. Okay. The ReLU is not differentiable at that hinge point, but it's very simple to differentiate everywhere else, right? It's a linear function. I don't do anything if it's large, and if it's less than 0, it's 0, so its derivative is also 0. So I just need to have kind of a if condition inside there. So it's pretty easy to deal with, but it's not continuous. The sigmoid is differentiable and easy to work with so derivatives. So I want to do this in the fire or not fire to make this so it's continuous. Okay, so now what is a neural network? It's going to take these neurons plus activation functions, and then I'm going to chain all these things together. I'm going to put this in some sort of structure. So a network. Okay, I'm going to have as input, this is my input X, this is going to be an RD, and then I'm going to kind of draw this as a diagram here because it gets very complicated, right? But I'm going to think of one, so neuron, this is one, so this is one neuron, which is this linear classifier, and I get a value, and I'm going to put an activation function at the end, right? So this is the output of this is going to be a kind of a value which is so continuous. If I used a ReLU, I know it's greater than 0. If I knew a sigmoid, I know it's between 0 and 1, and typically near 0 or 1 if it's a sigmoid, but it might be in between. I want to be differentiable in between. Okay, and so I want to chain these together, but kind of the first observation is that instead of just doing the one after another, I'm going to have an output, which is going to be, say, it might be a k-dimensional output. And I'm going to take from the same input and repeat this many different times. I might be taking all of my data. So this might be k equals 4. I have 4 of these neurons from the same input, right? And each of these will have usually the same activation function. Right? Okay. And then I'm going to have, what I call this in my notes, we'll call this, H. This could be H1, H2, H3, H4, right? So I would have an H vector, which is in RK, right? So I have 4 outputs here, and now I can build more neurons. On the same data, and then I put activation functions on the end here, and again these have outputs, and this has another layer. Okay, and I can repeat this process, right? And I need the activation functions. Okay, and we'll see why these activation functions are so important. Okay, so all right, so what I'm going to call this the set of these neurons, so W. Okay, so like uppercase W here, and this is going to be in I'm going to write this as a matrix that's D by K. Actually, let's flip those around. K by D. Okay, so we're going to think of this as a matrix that is going to be W1, W2, W3 up to, so WK. Each of those is a weight vector in our D, right? So each of these, each WJ, or there's lots of subscripts and notation in these things. It gets quite overwhelming. So each of these is an RD. Okay, right? These were the dot products I took, right? These were the dot products I took. If I wanted, sometimes I have this bias vector B, and I keep that as well. That's an offset. But let's ignore that from now. I can encode an extra 1, and there's a variety of things, right? So these are the weight vectors. And there are K different weight vectors. So W is a matrix. And so to get before the activation function, right, I could have W, this could be W1, I can have W2, W3. And so what I'm basically doing is to get to this layer in here before the activation, this output here, let's call this A. A is going to be equal to W times X, right? I can encode all the dot products as a matrix, some multiplication. And if I didn't, or as W1 times X, right? So A is then in RK, right? But it hasn't been through the activation function. So if I didn't have the activation functions with no activation, okay, what I can write is this is going to be, this is A1, I'm going to have A2, this is A3, then I'm going to have A3, or let's say, if there's no activation, then A2 is just going to be W2 times W1, right, times X. And A3 is going to be W3 times W2 times W1 times X. Okay, and I'm going to learn the parameters of the W. Those are my parameters. Okay, so why is this not very useful? Because I can write a single matrix, let's call this B equals W3, W2, W1. I can write a single matrix, and that can do the same work as these 3 matrices together. Okay, so if I don't have the activation, I might as well just learn one matrix. The extra matrices don't give me any more representational power if I don't do some sort of nonlinear activation in between. All right, so the activations are essential. Otherwise, you're just finding like these linear regression or these linear models. Okay, at the end, yeah, I'll say also at the end, I want to just put one additional neuron, and then I have, so some threshold. I don't need this can be, I take the sign at the very end, right? So at the very end, I get an output and I take the sign, and that's my classifier, right? So at the end, I put a linear classifier on top of all this, but I chain these things together, right? And I put these activations, this non-linearity makes it more powerful than just stringing them together by themselves. That's why I need these activation functions here. Okay, and then a lot of design in neural networks is the right way to kind of structure this. I don't necessarily put all of the connections. I could put subsets of the connections, right? A convolutional neural network assumes the input is structured, usually as an image, and then just takes a bunch of a neuron just on a patch of the image at a time going forward. And those patches get bigger over the layers, right? This is one example of an extension of this sort of framework. Okay, so if we want to learn the neural network, what is it we have to learn? We have to learn all of the parameters and all of the W's. Okay, usually we fix the structure of it, we choose an activation function, that's fixed, and then we have to learn all of the W's. These are the parameters. It's a lot of parameters, okay? These neural networks are over-parameterized. They seem like they should be overfitting on data. And to actually get them to work, you kind of need to do a bunch of tricks so they don't overfit. And those are different from the sort of tricks you typically would use in like polynomial regression or polynomial classification. There are other classes of tricks you need to use. I'm not going to go into this. Okay, but I need to learn all these parameters W's, learn these parameters. It's probably on the final. How would you learn a bunch of parameters of a function? Yeah, we're going to run gradient descent. In fact, we're going to run stochastic gradient descent because the computing the gradient is going to be very time consuming. So we just want to do it on one data point at a time and update everything, and then see another data point and update. So stochastic gradient descent is going to be the backbone. Okay, we have to compute, to do that, we have to compute the gradient over all these parameters, right? This seems hard. The trick to making this work is what's called, so there's this trick called, propagation, okay? And so in the last couple minutes or 2 minutes, I'm going to try and explain this roughly. When you read a piece of data, it goes through the neural network layer by layer. At every point, you get these outputs at like the H layer, right? That's H1 layer, then H2 layer, then H3 layer. And then you get to the end and you compare it to the sign, right? Only on the last point do you compare it. Did I make an error or did I not make an error? If you made an error, you want to update it based on some loss function. You put a loss function on the sign, and you can take a derivative. And in fact, these last weights, these are easy to learn, just the ones in the last layer, right? I can say, well, if I just want to learn those weights, I assumed that if I put in a value X, it pushed all the way to the last layer, and then I can just learn the linear classifier as an extension of what we talked about earlier, right? Pretty straightforward. But I also need to learn the weights in this layer, and this layer, and this layer. And the idea is start with these layers, and then back propagate to here what how much air was there on each of these coordinates? And I use that to treat each of these individual neurons like a single sort of linear regression, where I can just individually compute the gradient of that neuron by itself. Okay, and I go backwards, I push a data point forward, make a prediction, and then I walk backwards and figure out what the gradient is. And you can decompose the gradients using partial derivatives. Okay, and so what you end up getting is a function. This g of x function looks like w1 of x times some activation function times w2 of the output of that activation function, right? Right, and then I pass this through another activation function, and w3 times this activation function, right? This basically gets me to the last layer, and then maybe there's another single layer here, w4. Okay, so this is what the neural network looks like, where this is w4 things. Okay, and w4 might be a vector, and I can take, basically what I want to do is take the partial derivatives of just this one. This one is easy to compute the partial derivatives of. Then given that value, I play the same trick and calculate this one, and I update the gradient on W3, and then I do this, and I update the gradient on W2, and so forth, and update the gradient on W1, and that's how the backpropagation works, and in a nutshell, without going through all the math. Okay, and so the fact that we're able to structure these in layers allows us an easy way to take the derivatives in this way. And the activation functions are essential to make sure it's not just a single linear classifier, because things would cancel. Okay, we'll kind of stop here. There's if you want to learn more about this, there's a whole class in machine learning. There's a class in deep learning where they talk about how to structure these and how to build a bunch of stuff. There's a lot more to do after this class. This is your introduction to that. All right, I'll see you on Thursday, and we'll go over the practice final. Suggest you look at it before class. Homework 4 should be done being grade 1. Yes.